Hello everyone, welcome back to the another session in design and analysis of algorithms. The topic name is backtracking. Video will be going to talk about the algorithm, how n queens are getting placed in n by n chessboard. So that part we'll see, and also we'll cover the generalized method of recursive and iterative to place the queens. Now let's get started. We discussed in the previous video what is n queens problem. Now I'm going to take the algorithm. According to this algorithm, we'll place n queens. So n queens means you n by n chessboard. If my n value is 4, I have to take 4 by 4 chessboard to place 4 queens in such a way the queens should not be no row, no same row, no same column, no same diagonal. If this n value is 8, then chessboard dimension should be 8 by 8. If this n queen is 6, then chessboard dimension should be 6 by 6. This 8 or 4 or 6 represents how many queens you are going to place. Placing the number of queens, and this number will tell you what is the dimension of your chessboard. Both things will come in the same figure. Now, so the reason basically why I am talking about 4 queen, I can take any example, but the reason I am taking 4 is what? If I take 4 queen problem, the number of possibilities that I can place queen in this chessboard is 16c4. Okay. If I take 8 queen, the number will get proportionally change, correct? If I take 6 also, it will get increase. So if I talk about 4 queen problem, you people can understand easily. Whatever steps I am taking to solve 4 queen problem, the same steps you can take for 6 queen, 8 queen, n queen. I have to place the queen in this board in such a way, no attack. Keeping in mind this principle will be working. No attack in the sense what? If I place q1 here, you cannot place these, correct? All these are block. That is what the problem. When you given with 4 queens, no 2 queens should be same row, same column, same diagonal. If 1 queen is already here, this cell is blocked. You cannot place q2, you cannot place q2. This diagonal path also block. So this is where you can put the other queen. Let's assume that I am placing q2 here. Then again q3 cannot be here, q3 cannot be here, correct? And even q3 cannot be here. So while you are placing a queen in the chessboard, you have to put these constraints in the mind where you should not have any attack. That's what no attack. So first algorithm, this piece of code will help you out to find out, to place the k queen into the grid or into the n by n chessboard. This is what placing the next queen. If I wanted to place the queen, so concentrate here, I am taking k. K represents the row, I represents the column. Now, if I wanted to place a queen in kth row, ith column, that means in first row, first column. If I place q1, then these cells are blocked, correct? So what we are going to do is, we'll be going to iterate the loop from j is equal to 1 to k minus 1 do. We'll iterate this loop to place the next queen. Now x of j double equal to I. This is my pseudocode, so I can use single equal to, but it sounds that it should be an equalizer symbol. X of j double equal to I, in the sense my queen, what I'm going to place newly, that means already q1 is existed. Now I wanted to place q2. When you wanted to place q2, you have to make sure that these two queens are not in the same row, okay, or in the same column or in the same diagonal. You have to make sure this. So this absolute value will be going to give you the diagonal path. So it will tell you the no diagonal, no same diagonal. It will tell you the no same column. Now, if it matches, then we'll return false. If it doesn't matches, then it says that indirectly that queen is under no attack. That means we return true. Now let's see how n queens will work. Algorithm place k comma I. Now here in this, place is what? Place is a function where it will performs you that it will return if a q can be placed in kth row and ith column. That we were discussed just the moment, right? Now, so this is what? This n queens is the solution for all type of n queens problem. That I told you, that 4 queen, 8 queen, 6 queen, for all type of problems, this is the solution, or this is the algorithm what we will prefer to give the solution. Now, using backtracking, this procedure prints all possible placements of n queens using an n by n chessboard, so that they are non-attacking. Now, for I is equal to 1 to n do, if place k comma I, then x of k is equal to I. If k is equal to n, then write x 1 to n, else n queens k plus 1 comma n. Now, at this point, we might wonder how effective function n queens is over the brute force approach. For an 8 by 8 chessboard, there are 64 8 possible ways to place 8 queens, or approximately 4.4 billion 8 tuples to examine. However, by allowing only placing of queens on distinct rows and columns, we require the examination of at most 8 factorial. And to get this, these are what possible, that maximum number of nodes what I can get. And this is what using backtracking approach. And this is what maximum number of nodes, and we will be going to get using backtracking approach and applying bounding function. You'll get 4 factorial. Now, so let's see how it will be more effective by tracing this for each cell. Right now, let's assume that it is n by n chessboard, that I am taking 4 queen problem, so it is 4 by 4 chessboard. How algorithm will work is, initially we will be placing the q1 over here. So when I place q1 here, now you cannot place this row, this column, this diagonal you cannot place. So obviously my q2 should be here. This is the place of q2. If I place q2 here, again this block, this will get block. Now I can place only q3. Look at this chessboard. After you place q3, you didn't find any place to place the q4. So that's what we will come to this q1 and we'll change our decision. So what is backtracking? Backtracking is what? While you are generating the solution, when you feel that it is not giving the solution, we'll come back. We'll go back. Let's see. q1 I am placing at first column. So here we'll take only the column values. We will not consider the row values. The reason is, when I place q1 here, I told you that 3 constraints: no same row, no same column, no same diagonal. So what we'll do is, the first row we'll give for q1, the second row we'll give for q2, and this is for q3, and this is for q4. So we fixed the rows what to be there, which queen has to be there. Now the problem with the what? Columns. Which column I have to arrange for this which queen? That is what the problem. So that's what we will do is, we will talk about the column only. So how we will proceed is with the state space tree. Now what is state space tree? Will generate all possible of E nodes. Will elaborate the nodes with the possibilities. Now this is my root node. Now what columns I have? Columns are, I can place Q1. This is my root node. I can place Q1 in the first grid or first cell, or else I can place in the second cell, or in the third, or in the fourth place. That means I am talking about this. So this is what your column. You can place here 1, you can place 2, 3, 4. If you place here Q1, your Q2 can be in the second column, no. Third, Q3 can be third column, Q4 can be fourth column. Here I have to write. If I place Q1 over here, Q2 should be this column, Q3 should be this column, Q4 should be this column. Now, if I place Q1 in the first place, first column, now my Q2 is in second column, my Q3 is in third column, and Q4 is my fourth column. Obviously, this way of putting the solution into your chessboard or n by n chessboard will not give a proper solution, because I told you it should not be in the same row, it should not be in the same row, same column, same diagonal. So it is one of the solution, but it is not the solution. What we'll do, when you fix that it is not the solution, we'll backtrack, and that's what the backtracking. So when I'm talking about this, you can remind brute force approach. So brute force approach is also what? It will generate you all possible solutions, correct? So now backtracking is what? It's just like of brute force, but backtracking will provide the solution. Once the solution is not giving the feasible, you'll backtrack. You'll backtrack to the upper node, where you feel that this is not the solution. So that is the difference between brute force and backtracking. Now let's see how this function will work. So when I wanted to place Q1 over here, so that means I have placed Q1 in the first column. So I have root and I came for second node generation. So the second node is what? That is Q1 is at first column. So now when Q1 is first column, you cannot place Q2 in the first column. Q2 can be in the third column, second column. So I am placing Q2 here. If I place Q2 here, according to the condition, it should not be in the same row. So what I will do is, I will again check for Q3 and Q4. So this is not proper solution, we will backtrack, and here we will take other turn that I am placing at third column. So like this we will generate state space tree. Okay, now how it will get work, that we'll see with the recursive approach. Now before we go to that recursive and iterative, let's find the definition for bounding function. What exactly the bounding function, how I can reduce the complexity from 16C4 to 4 factorial. So that is what using bounding function. Bounding function is what? These are used to kill live nodes without generating all their children. So that's what we were discussing, right? When I wanted to place, it is my root node. When I wanted to place Q1 in the first column, now Q2 in the second column, Q3 in the third column, Q4 in the fourth column. So like this, you will get total 16 C4 possibilities. So what we'll do is, when it is not giving the proper solution, we'll backtrack. That means we'll backtrack and also we'll apply bounding function. What is bounding function? We'll kill the node not to elaborate. We'll kill the node not to explore. So we'll kill this procedure here, because when first column is filled with the Q1, obviously your Q2 should not be down of it, right? So we will backtrack here and we'll change the solution. That means my Q1 cannot be in the first grid. Q1 can be in the second grid. Okay, now, so what we'll do is we'll apply bounding function and we'll kill the nodes not to generate the children node. Now, depth first node generation with the bounding function is called backtracking. We have the other approach, branch and bound. That's also uses state space tree. That's also uses bounding function, but that will use depth first. It will use breadth first. That's it. So applying bounding function is same in backtracking and branch and bound, and killing the nodes is also same. And drawing the state space tree also same. What is the difference? The difference is backtracking uses depth first search, branch and bound uses breadth first. That is the difference. Now let's see how backtracking generalized recursive approach. So our intention is what? We wanted to solve the problem using backtracking, correct? So recursively we'll apply it. What is recursively we'll apply? We'll apply to get the solutions recursively. So that means we'll call the function for each time. So when you apply sum 1, 2, 3, 4, these are what column and values, right? Now if I feel that fourth queen is not having the solution, again we'll recursively call the function to place the other queen at other place. So this is what recursively happens. Now iteratively, how it happens is we'll take one loop and we'll go for successful finding the queen position or unsuccessful finding the queen position. So we will be having in the state space tree both. So state space tree, what it will do is it will be going to generate all possible nodes. So we will cut at one level when it is not feasible. So it is iterative approach, and that is what recursive approach. So now let's see this formula and we'll close this with the formula. When you are generating a state space tree, how many maximum number of nodes you will see? To calculate that we have a formula. Now let's see this one. It is what? 1 root node. So 1 plus. How many nodes are there in the root node? 4. 4 plus. Down of this node, how many you have? 3. 4 into 3. Because each element is having 3 under it, right? So like this you have 4. So that's what 4 into 3. The next is this element is having 2. That's what 4 into 3 into 2. And the next each 2 sets are having single element. That is 4 into 3 into 2 into 1. So now the formula to generate maximum number of nodes is 1 plus, from this to I am applying the formula. That means 1 plus sum of I is equal to 0 to 3 and product of j is equal to 0 to I, 4 minus j. This 4, it will indicate that the 4 queen problem. If it is 8, then in the place of 4 you can write 8. So this is what maximum number of nodes. So this is about backtracking algorithm and backtracking with recursive and iterative. Thank you all.